Howdy. Howdy. Okay. How has studying been going? I would hope that you had studied a little bit before coming to this. Yes. So I've had a lot of questions about this. Quiz 5 was that one that you were basically just giving feedback like about the class, and it was the take-home one. That one will get fixed to be full credit before your quiz grades get averaged for quiz 10. So don't worry about that one. It's just going to be like done last on his list. Are there any other like general questions? Yeah, what's up? What do you mean weighted? That should already be plugged in. Any other general questions? Okay, I had uploaded these questions earlier today to Canvas, so I hope you guys are able to see them and maybe start thinking about them. Yes, no, maybe so. Okay. Uh, Today I'm going to cover like a review of basically everything up to exam 2, and then tomorrow will be stuff that we've learned since exam 2, because the exam is cumulative. So, oh, also, I posted videos for the homework, or for all the homeworks, a video for the homeworks. It is 2 hours long. But I put the time codes in the comment section so you can click to like specific homeworks to try and if there's one in particular that you want an explanation for. Okay, so the first set of problems I have for y'all, or the first like few questions, is throwing back to pKa. So you will have a pKa table on the exam. It's this one that like was on all your other exams as well and was in the lecture slides. So we'll start out with taking these 4 structures and identifying the most acidic proton. And then you can, or we will, go through and look at the pKa's, rank them, draw the conjugate bases. What's up? What is it? Lecture 8 is the one that has the pKa table. Okay. So, do we feel thumbs up, thumbs middle, thumbs down about pKa? Okay. I'm seeing mostly middles and ups. So, we'll start with this one. First of all, what functional groups do we see here? An alcohol is not looking at the full structure, though. A carboxylic acid. And then what's special about this ring? It's benzene. What like property makes it special? It's aromatic. So if I were to draw out all of our implied protons, how many am I missing from this structure? Five. So now we have all of our options drawn out. Which of these protons will be our most acidic proton? Hmm? Anyone have a confident answer? Yeah, exactly. So carboxylic acid, it's in the name of the functional group, it's an acid. And so that proton will be our most acidic of these protons. So moving to our next one, what functional group do we have on this? Yes. How many implied hydrogens am I missing from this one? Mm-hmm. 11. So now that we have all our protons, which one is the most acidic? Can you say why, or do you know why? Do you have a why? What's up? Mm-hmm. Mm-hmm. So this is our most acidic proton. And usually you'll find your most acidic protons next to or attached to a heteroatom of some kind, or a carbanion of some kind, or carbocation of some kind. And we can look at our pKa table for lots of examples of acidic protons. Okay, what about this next one? What functional group do we see here? Yeah. So that one is attached to our heteroatom. And we can also look at our pKa table. And is a more acidic proton going to have a higher or lower pKa? Lower. So pKa, the number with pKa is basically telling us the strength of this bond. If it's a low number, that bond is not very strong. That means the proton can come off pretty easily. So we can look at our pKa chart for comparisons on numbers. And just by rule of thumb, you can know to start with looking at those heteroatoms, which is like a heteroatom is anything that is not carbon or hydrogen. So sulfur, oxygen, nitrogen, phosphorus. Does that help? Okay. What functional group do we see here? Mm-hmm. When looking for this on the pKa table, if any of you have it up in front of you, is this the structure that is under amine, or is there another word that we should be looking for? Yes, whoever said that. A protonated amine. Because we have one extra proton giving us that overall positive charge. So how many implied hydrogens are we missing in this structure? I see more than 5, 7. So out of all of these, which is our acidic proton? Yeah. Yes, any of the hydrogens and the nitrogen. You could circle one of them, you could circle all 3 of them, you could circle 2 of them. Any of that combination would be correct. Okay. this last structure here, I won't ask the functional group question because I don't think we've learned the name for this functional group. Oh, but we do know the name for that functional group. Say it louder. So you're half right. Phosphate diester. Do you know what the like root? Yeah, root of di is 2. So this is just phosphate. Diester would, or what is an ester as a functional group? So if it was inside a carbon chain, we would have an ester, but this is not with, like, there's not another carbon coming off anywhere. Okay. How many implied hydrogens am I missing? We are missing 7. So with all our hydrogens drawn out, which one is our most acidic? Yeah, the one on the oxygen. Yeah. So an example could be like the proton next to a cation. It's on a carbon, so oftentimes we won't draw it out. But these ones that are adjacent to the cation, those would be the most acidic. Other questions? Okay. Can you guys estimate pKa? What is the pKa of our carboxylic acid here? Yes. What about the pKa of a thiol? Yeah. Yes. So the pKa chart, it does have some like full acids drawn out, like sulfuric acid, hydroiodic acid, and there are some other ones on here, but for the most part, it's just general functional groups. What's up? Mhm. Not in our case, no. So that is why when you're looking at this, you don't want to say it's just an alcohol, because the pKa of an alcohol and the pKa of a carboxylic acid are very, very, very different. So you want to look for the best match functional group, which means sometimes looking at the whole molecule, but we don't have any kind of like benzoic acid on there. So what's up? So if there's two functional groups on your molecule, then you can use your pKa table to identify the pKa of each of them individually. And from there, identify which one is more acidic, because there will be one that has a lower number. But that's a good question. 10.5. What is the pKa of a protonated amine? And finally, this phosphate. I don't know if that one's on there actually. Okay, we'll skip that one for now. So now that we have our pKa's, can we rank them in order of increasing acidity? So which is our least acidic? 10.6. Next would be, and then, so if we wanted to do the molecule structures or the compound numbers, we could say 3. Okay, so drawing the conjugate base for each compound. What does it mean to be a conjugate base? Yes, the proton is gone. So we can take our structures and draw them the exact same way, just now without that proton that we labeled as our most acidic. Because the proton left, but it didn't take the electrons with it, we will always have a negative charge where we were neutral, a neutral charge where we were positive. So both of these were neutral originally, but our protonated amine will now be neutral. Okay. So now we can predict the equilibrium using the pKa. So which way will it go? Towards the sulfur being protonated or the carboxylic acid being protonated? Towards the sulfur being protonated. Why? Yep, the stronger acid will more readily lose that proton. So you can kind of think of it as we'll always point at the higher number. But if you're going to think about it that way, you want to make sure you're always writing your pKa under the protonated form. Okay. Questions on that? What's up? Okay. Okay. So acid and base, what is the relationship between an acid and a base? Well, so the difference between an acid and a base is one has a proton to give and one is able to take a proton. And so when you have an acid, drawing the conjugate base means you're just drawing the base form of the acid. And so the only difference there is whether or not that proton is there. So if the proton is there, it's the acid. And if it isn't there, it's the base. We say conjugate because it's the same form. If we were doing this kind of question with like bases, we could have drawing the bases and then drawing the conjugate acids. But it's basically just the difference between is the proton there or not. Does that help? Okay. Other questions on pKa? We've had lots of questions about them in class, so I recommend reviewing them, making sure that you have them down. What's up? Yeah, so the way that I approach the equilibrium questions, usually the equilibrium question will have the same compounds that were in earlier parts of the question. So you'll already know what the pKa is. So I will write my pKa under the acidic form, so the form that has the proton on it still. pKa is basically an indicator of how strong the bond holding onto that proton is. If it's a low number, that bond is not very strong, and it will lose that proton more readily. So if it's going to lose it more readily, that means the equilibrium will favor the side where the proton is lost. And so our carboxylic acid has a much lower pKa than the thiol. And so that is the one that we would expect to see deprotonated instead of protonated. What's up? Mm-hmm. Yes. So this is acid base. Before I get into the other parts of the bonus question, do we feel confident on identifying pKa's, identifying acidic protons, and drawing conjugate bases? Thumbs up, middle down. Okay. So yes, the reaction type is acid base. Now, if we were doing disconnection at, oh, what's up? So you can use your pKa chart to help with that sometimes. So like a protonated ketone will have a very obvious proton. Some of the other ones won't have as obvious a proton. So one of the examples I already talked about was just like any carbocation where the protons may not be explicitly drawn out, but we know from class and reviews and our pKa sheet that the carbons next to a carbocation will have acidic protons. Another example of this is this diketone. I don't have any protons drawn out here, but can you take a guess which carbon will have acidic protons? The middle. Why do you say that? Do you have a scientific reason to bolster that? Do you want to phone a friend? We have someone in the front who is volunteering. It is because you can make more resonance structures. So once you have your conjugate base, you can delocalize those electrons up into either oxygen. Whereas if you picked one of the carbons that was on either side, you would only be able to delocalize into one. But if you pick the one in the middle, you can delocalize into both. So the most acidic proton will not always be the one that is explicitly drawn out. Any other questions? Okay. So disconnection analysis with this. We'll say doing it in the direction of equilibrium. What bond will I break? Doing the reaction in the other way. That is true if we're doing it left to right, but if we do it in the equilibrium favored direction, we'll be doing the reaction right to left. So what bonds would we break on the right side? This one. So what kind of star species do I need to draw? What kind of star species do I need to draw? The like things that have a little asterisk to them. Mm-hmm. Exactly. And I kind of already have them reorganized in the way that makes sense. So then what else do I need to complete this disconnection analysis? What else do I need to indicate? Bonds formed. And what bond is formed? For the sulfur. Do we feel good about that? Okay. So the next question is an NMR question. And there's a lot of breakdowns to this. We want to assign the compound to the correct spectrum. We want to assign all our signals. And then we're also going to look at disconnection analysis and identifying the reaction type. So where do I start? Mm-hmm. How do I know which one is the site? What makes up a site? What exactly am I looking for? What kind of atom? Hydrogen. So really our first step should be drawing out all of those hydrogens. Am I missing any? Yes, no? Okay. So with all of our implied protons drawn out, how many signals would I expect to see from this structure? Yeah, 7. How should I break up my aromatic proton? The ones next to each other or the ones across from each other? Across from each other. Why can I group these together? Yes, because this is symmetrical. So they see the same thing. They're chemically identical. Now that I have all of my proton signals identified, what's our next step? Mm-hmm. And what does that tell us on our NMR? What's the fancy word for it? Close. It is an I word. Anyone? Our integration. So it tells us the height of the peaks. So A is going to be how tall? B is going to be how tall? C is going to be how tall? D is going to be how tall? 3. E. F. G. Okay. What is my next step now? Anyone? Yes, we're going to figure out the splitting. How do we figure out the splitting? Looking at our neighbors. So what splitting would we expect to see for signal A? Why? It has no proton neighbors. Oh. Okay, what about B? Doublet. We have one neighbor. What about C? Doublet. Again, we have one neighbor. What about D? Singlet. Why? We have no neighbor. Okay, what about E? It's also going to be a singlet. What about F? A quartet. And what about G? So now we can look at our chemical shift, which I am going to pull up the chemical shift table. G is a triplet. That's what the T is. Okay. So what's up? Yeah. So this is the carbon that has our protons for signal F. If we look to our neighbor here, there are no protons. So we have 0 neighbors here. But if we look to this carbon, we have 3 neighbors. And our rule for splitting is always +1. Because if it was just how many neighbors you have, our singlets would be nothing. So we have 3 neighbors, +1 is 4. So we would expect to see a quartet. Okay. So with the chemical shifts up there, what would we expect A to have a chemical shift of? Anyone? It is up there. Look at what it's directly attached to. 3.3. Okay. What about signal B? Where would we expect those chemical shifts to be? 6.5 to 8. What about C? The same. What about D? .85. Or actually, there's a better answer on there. It's kind of hard to see. It's 1.7. But what you just said helps with E. So what's the chemical shift for E? 2.4. And then what about F? Anyone? Why? But is the proton we're looking at directly attached to the same carbon as the double bond? 2.1. And what about G? .85. So if you had an NMR question on the exam, you should know how to do all of these steps, and be able to report how many protons are in the signal, how many signals there are, what is the splitting, and what should your chemical shift be. So now that we have this molecule completely annotated, we can look at our NMRs. Which NMR, the top or the bottom one, better matches what we've just annotated compound 3 as? Oh, question, what's up? Yes. So on our chemical shift chart, we have this one where it is protons on a carbon next to a double bonded oxygen. So, top or bottom? Top. Now we can go into each of these signals and start labeling the signals to the proton groups that we just made. So with our aromatic ones, you guys don't have to separate those. So we can put BC for these ones. What is that next signal? Which one do we have that is one proton? E. Which 3 protons groups do we have that are singlets? Which would make more sense to be this peak? Why? So we can see that sometimes these exact numbers of where we see it on the graph don't match our chemical shifts that we predict. Do you guys know why that is? Yes. In this case, oxygen is our only heteroatom, but being next to things like oxygens or nitrogens, those kind of electron hogs, is going to change our chemical shift value. So this little 2H, which signal is that? And then what's our last one? G. So when you have an NMR question, this will be exactly what you do. You'll have to annotate the molecule and show that you know each of the individual steps that get you to where you can annotate on your NMR which molecule is which. Do we want to walk through this same process with compound 4? Or do you guys feel like you got it? Yeah? Okay. So, oh wait. So now, what reaction type is this? It is not. It is not. Closer, but also no. It is an aldol. So, for an aldol, we need 2 ketones. For a claisen, we need 2 esters. What do we have here? 2 ketones. For acid base, all we would expect to see is a proton changing. This is much too complicated a reaction mixture to just be acid base. And with elimination, the only change we see is the formation of a new double bond. Knowing how to recognize reactions is going to be a very vital part of this final. So I really recommend breaking down the study guide and breaking down the slides into ways that help you guys understand and recognize reaction types. Sometimes that's most helpful by like doing disconnection analysis and doing curly arrow mechanisms. Sometimes it helps to do flashcards where on the front you'll have the reaction type and on the back, like for aldol, you could say 2 esters and they make, well, for an aldol addition, it would be a ketone or 2 ketones, and it makes a ketone and an OH, an alcohol. If it's an aldol condensation, it's 2 ketones that go to a ketone and a double bond. And then you can start recognizing them more quickly. What's up? Yeah. Mm-hmm. Mm-hmm. That's what an acyl group is, or carbonyl group. Mm-hmm. Other questions? Yeah. 8. Total. There will be 8 questions on the file, much like there are 6 questions on all your prelims. 2 hours. So how can we do disconnection analysis for this? We'll start with drawing out our starting materials. Where should I put my bonds broken? Can you be more specific? Actually, I'll ask a precursor question. Do I have all the necessary things drawn here to do our disconnection analysis? Why do you say no? Yes, that was not what I was getting at, but is true nonetheless. Any other things I'm missing that would be pretty important for disconnection analysis? What's the first step of aldol condensation or addition? Yeah. Deprotoning. Do I have any protons here written that I could remove? No. I need to draw in some protons. I don't want to scare you guys, but the lack of participation does have me kind of worried about your understanding of things. And it's okay if you don't know the answer, but to ask questions is also important. How many protons should I draw off of this carbon? 3. So to get to product 3 that I've drawn here, which proton should I remove? Should it be off compound 1 or 2? Compound 1. What's up? Because it would be a different disconnection analysis right now. So that would be our first, what's up? Most of the protons drawn on the first one are not necessary either. But I can draw all of them if that is more helpful. I drew in those ones because we were working with compound 1 first. Does anyone know what the reaction mechanism for an aldol condensation is? Okay. Our first step with aldol condensation is always going to be deprotonation using our base. That will create what? An anion. Would you say an anion is more electrophilic or nucleophilic? Nucleophilic. Do we have any spots on our other molecule that are electrophilic? Yes. So we have a difference in polarity between the carbon and the oxygen that is going to make that carbon center a little bit electrophilic because the oxygen is hogging those electrons towards it. So our nucleophile can attack our somewhat electrophile, and we can push the electrons up onto the oxygen. Does anyone know what this intermediate is called? What's up? We're going to cover the curly arrow mechanism for this one, and then we can go back to disconnection analysis. So what is this intermediate called? It has a fancy name based on geometry. Yeah? It's called a tetrahedral intermediate because this carbon is now tetrahedral. So now, when we took our proton off, we created the conjugate acid of this base. And we can make our alcohol. If I stopped here, what reaction would this be? Addition, aldol addition. But do we have an aldol addition here? Is this our final product that we see via NMR? So next we have the part that makes it a condensation. Any guesses what our next step is going to be? Yeah. Not off the hydroxide. So this is going to follow our elimination reaction, but it's not just like E1 or E2. We have a base. So we're going to do E1CV. So what's the first step of E1CV? This was an exam question on exam 2. Deprotonation where? I'm off by 1 carbon here. It will not be on. Where will it be? Okay. It will be much like our first step of the aldol addition. It'll be next to a carbonyl. So now we can kick off water, or OH minus, to form our double bond. And to keep our base catalytic, we have to also take the proton off of there. And that's how we get finally to water. So aldol condensation is kind of a mix of two different Corelliero mechanisms, our aldol addition and then E1CB. So back to disconnection analysis. We definitely have to take that proton off. What else will we? This methyl group is that methyl group, just drawn at a bad angle. If we're making water, we have to lose a pretty important atom, oxygen. Is it going to be the oxygen off of compound 1 or compound 2? Compound 2. How many protons do we need to make water? 2. How many have we currently drawn disconnected? So we need another proton from somewhere. Any thoughts on where? Yeah. Yeah, the same methyl group. So then we can draw out our star species. Now we can indicate what new bond was formed. And which bond would that be? Which bonds multiple? Those are definitely 2 that get made. And the double bonds that we form. So aldol condensation and addition are both good examples of CC bond creation. And we make a carbanion. E1CB, we make a different carbanion. questions on this? Yeah. So you'll see that the oxygen has 2 stars because we'll make 2 bonds to 2 different hydrogens. And the carbon that we separated it from also has 2 stars because we'll end up doing a double bond to the other carbon. So, no questions on this? Okay. You had a homework question that was very similar to this. Redraw the reaction using the given substituents. First, what kind of reaction is this? Claisen. How do you know it was Claisen? Rather than fill in which R groups will be R1, R2, because there's so many possibilities of answers for this, I think it's easier to give like R1 is now equal to R5. Do you guys understand what I mean when I say that? Yes? No? Okay. So in our starting material, we have R1, 2, 3, and 4. And our product, we now have 5, 6, 7, and 8. The purpose behind this kind of exercise is to see if you can map out where each of these R groups ends up in your product. So 5, 6, 7, or 8, one of those is R1, just now after it's been reacted. So which one ends up as R1 or started as R1? In that case, which one is R2? Oh, it's not R6. Also not R7. Do you see how R1 and R2 were connected to the same chain? If we were to highlight that, and you said that this is your R1, you would expect there to be an oxygen right here. But there isn't. That oxygen was lost, and with it, the R group attached to it. Then we look at our other structure that has R3 and 4. Yeah. Yeah. So you could also do so instead of redrawing, this is the easier, faster alternative. Now we can do disconnection analysis with it. What bonds need to be broken? Yes. Is it the only bond that needs to be broken? What else needs to be broken? On R3 or next to R3? Do we need to draw any other bonds broken? Okay. How many star species do we expect from this? 4. What newly formed bonds should I indicate in our products? Which one? Which side of the alcohol? To the proton or to the carbon? Mm-hmm. What else? Did we make another bond? Does everyone agree? Does anyone have questions? Yeah, I would draw it at least once as like drawn on there, but then you could abbreviate it. Like I would draw it on your starting material and your end, but the intermediates you can just abbreviate as R1. Okay. Where do I start? Yeah. Yes. Where do we start with a curly arrow mechanism for this? Deprotonate, which one? Yes, but I mean like the R1, R2 structure or the R3, R4? What will be responsible for that deprotonation? Base. what would we call this intermediate? Now that it has this negative charge. Carbanion. And would we say this carbanion is nucleophilic or electrophilic? Nucleophilic. Do we have an electrophile around? Mm-hmm. It's the similar idea as the aldol, where we have this double bonded O that is making that carbon of the carbonyl a little electrophilic. What kind of intermediate is this? Mm-hmm. And what happens to tetrahedral centers? Are they stable or unstable? Unstable. So they'll collapse. And we have to kick something off. If we go up, we'd get back to where we were. But we can kick off this remaining up. What's our last step here? Is our base catalytic or one use only? Catalytic. So we have to restore it. And how can we do that? Mm-hmm. So what's up? For the same reason I wrote carbanion above this one, just because it's labeling what kind of intermediate it is. You don't have to do that on an exam, but it's to help you recognize the patterns in these reactions. So that is disconnection analysis and curly arrow for Claisen reactions. Are there questions on that? Okay. This should be a question that everyone should feel confident on. We've had one of these on every exam, on a lot of homeworks. We've had a lot of practice with this. Where do you guys start when you have a question like this? A ring. We don't want to do a benzene because benzene doesn't have any chiral centers. So now we can start knocking out our functional groups here. So what does phosphate look like? Basically a phosphorus surrounded by oxygens. What is an imine? Yes. What is an amide? Oh wait, let me go in order. What's an alkyne? What's an amine? That's an amide. NH2? Is NH2 the only option for an amine? You could also have that's also technically an amine. This is ammonia. Now, what is an amide? Okay, what about an alkene? Is the double bonded what? Yes. What is a ketone? What is an aldehyde? Very similar to a ketone. That's a carboxylic acid. What's up? Ketone does, so our ketone does have two different R groups. What if we didn't have two different R groups? What could we have instead? An O would put us as a carboxylic acid, yeah? Yes. So an aldehyde is basically the same as a ketone, except it's terminal on a carbon chain. So that means it doesn't have carbons on both sides. It only has carbon on one side. And what about a carboxylic acid? What about an alcohol? And finally, what about a thiol? SH. What else do I need to add to my molecule still? But can they be any old ring? What is an example of an aromatic ring? How many chiral centers do I have here? Any takers? 7. I have the 6 in the ring. Where is my 7th one? Hmm. If you know your functional group question or if you know your functional groups, this question is easy points on an exam that is worth 40% of your grade. What's up? Are there questions on this one? Did you get your question answered? Okay. What's up? Yeah. Okay. Other question? Yeah, what's up? So I have one ring here. They're not drawn proportionally, but they are both there. Other questions? Yeah. The very last page of my study guide has a pretty good list of ones to know. Phosphate is, I think, the only one that I don't have on here. Other questions? Okay. The next question is looking at resonance. What is resonance, first of all? Yeah. How our electrons can move through our molecule. What is more stable? More resonance structures or less resonance structures? Why? Yeah. So when you have more resonance structures, that means there's more room for those electrons to basically spread out or delocalize throughout your whole molecule. Electrons are very high energy, so keeping them compacted to a small space or only a few atoms could make the whole molecule unstable. But if we can spread them out across a long distance or a lot of the molecule, then the burden of that charge, of that energy, is shared more evenly. So, looking at these two, which of the carbon ions is more stable? Why do you say that? So, in the left, they can be delocalized through the benzene ring and to that carbonyl. Where can they be delocalized in the structure on the right? It can only go up to the carbonyl. So when we're drawing resonance structures, we show the movement of the electrons and we get this new structure. With our structure on the left, we could do the same thing as we did with the structure on the right and push it up into the carbonyl group. But what's that other functional group we have that we can push electrons into? Now accessible to us. I heard it whispered. The benzene ring. So there's a lot more resonance structures that we can make for this molecule over the other one. And that way, there's more stability and more delocalization. This last question, I think I'm going to save for tomorrow because I would like you guys to think about it. And I would like you guys to try your best at this question before we talk about it. I think working through this question will help you understand more of what you need to know regarding these reactions. This blank template of like all the questions is already up on Canvas. My study guide is already up on Canvas as well and has been for the whole semester. I really encourage looking at that before the final. What's up? Don't worry about it. You got bigger fish to fry, low-key. I will upload this as well, but how far up do you need? Yeah.